Hello everyone, welcome to chapter 4, summaries of bivariate data. For this chapter, we have two sections. Section 4.1, correlation. Section 4.2, the least squares regression line. So for section 4.1, we have two topics, scatter plot and correlation. For section 4.2, three topics. We will talk about the least square estimation, prediction, and interpretation. Let's now first start with section 4.1, correlation. The first part, 4.1.1, scatter plots. Data that consists of ordered pairs are called bivariate data. Let's look at an example for the bivariate data. So we have, for example, we have weight in pounds, and then we have height in foot. For weight, for example, 100 pounds, and then the height 5 feet. 160 pounds, 6 feet. 220 pounds, or 7 feet. And of course, we can have more data in each column. So this kind of data, we call that bivariate data. And the basic graphical tool used to study bivariate data is the scatter plot. So scatter plot is a XY axis plot. For example, we put weight here in the y-axis, and then height in the x-axis. And then we can label some scale here, like for height, we start from 4, and then 5, and then 6, and then 7, and then 8. And then weight, we could have from, so this one, let's say this is 100, and then 120, 140, 160, 180, 200, 220. Okay, that's good enough. Then we just put every pair there by x, y axis. So the first pair is 100, is 5 and 100, right? So 5 and 100. So put it here. And then 6 and 160 here, another dot. And then 7 to 20. So it's right here. So that's the scatter plot. Of course, if you have more pairs of data, right, we're just gonna have more dots from this scatter plot. Let's now look at this example. A real estate agent wants to study the relationship between the size of a house and its selling price. So this table 4.1 presents the size in square feet and the selling price in thousands of dollars for sample houses in a suburban Denver neighborhood. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 pairs of data. So the sample size is 8. So we should see 8 dots in the scatter plot, just like we introduced for this example. For each one, we label the dots in the XY system, and then we got this scatter plot. So if we look at the scatter plot, we can observe that larger sizes tend to be associated with larger prices, and smaller sizes tend to be associated with smaller prices. We refer to this as a positive association between size and selling price. In addition, the points tend to cluster around a straight line from lower left to upper right. We describe this by saying that the relationship between the two variables is linear. Again, let's look at this scatter plot. So we got the dots here. And then if we just put a straight line here, then we can see the linear trend, right? So all the dots, they're kind of clustered around this straight line and follow this line, right? Follow this trend. So we say this kind of relationship, the linear relationship. Let's look at some more examples here. So positive linear, that means as x value is getting larger, y value getting larger, and then it follows the linear trend. So then we can try to put a line here, and as long as the dots cluster around the line, then we say this is linear, and then we know this is positive linear. And same thing for this linear, the dots cluster around this line, right? But the difference is as x getting larger, y getting smaller. So we call this negative association. So negative linear in this case. And for this one, again, we can put a straight line here, right? The dots cluster around, no problem, it's linear, but the slope of the line is very small, right? It's not as steep as those two examples. So we say this is a weak linear. Then let's look at D, right? So it is a positive association. So x getting larger, y getting larger. However, it is not linear because if we draw a line following the trend of the dots, the data, then it is not a line. It's more like a curve. So I call this kind of situation from this plot D positive nonlinear. And then E similar. It's a negative association. As x getting larger, y getting smaller, right? And it is not linear. It's nonlinear. So E is negative nonlinear. Okay, that's some other examples. Now let's look at part 2, 4.1.2, correlation. When two variables have a linear relationship, we want to measure how strong the relationship is. We cannot measure how strong the relationship is just by looking at a scatter plot. And then we'll look at the example. So instead, we need a numerical measure of the strength of the linear relationship, which means it is not going to be affected by the scale of the plot. So let's look at this example, figure 4.3. So it's for the same data. But for the y-axis, the left one, we have from 400 to 500 scale. And for the right one, we have 200 to 700 scale. Although it's for the same data, but we can tell this looks more steep, and this one is kind of flat if we look at the linear trend. So this is also an example of the misleading graph. So by changing the scale, just look at the scatter plot, we got totally different information. So that's why the numerical measure is very important. So and the numerical measure we're going to use is called the correlation coefficient. So we calculate, just like mean, median, we calculate some number that represent how strong the linear association is. So R is calculated by 1 over n minus 1. N is the sample size. And equals number of pairs of the data. And then sum means add everything together. So x minus x bar over sx, y minus y bar over sy. So let's say we have let's just use the weight and height example. So let's say this is y1, y2, y3. So in that example, we have 3 numbers, each 3 rows, so 3 pairs, x1, y1, x2, y2, x3, y3, right? So we can expand this formula to 1 over n minus 1. So now 3 pairs means n is 3. And then sum means we take the sum of plug in different x values and different y values. The first term we have is x1 minus x bar over sx times y1 minus y bar over sy. That's the first term. And plus, right, take sum. So plug in all possible x and then take sum. That's the summation notation, right? So x2 minus x bar over xx times y2 minus y bar over sy. And last term, right? x3 minus x bar over sx times y3 minus y bar over sy. So after we list all possible terms, add it together and then times 1 minus 1 over n minus 1. And for this example, 3 pairs means n equals 3. And some properties. So now we know how to calculate. Let's look at some properties of the correlation coefficient. So correlation coefficient is always between -1 and 1. So R equals 1 means perfect positive linear relationship. R equals -1 means perfect negative linear relationship. And R is not dependent on the unit of the variable. And it does not matter which variable is x and which is y. So here we labeled x and y, right? If we change weight to x and height to y, it's the same. So it only measures the strength of the linear relationship. So the term linear here is very important. It is not measuring positive or negative relationship. It's the linear relationship. For example, this kind of data. If we calculate R, it could be close to 0 means there's no linear relationship, but that doesn't mean there's no relationship. So it doesn't measure how strong the relationship is. It's just whether it is a linear relationship. And this is sensitive to outliers. So if we have an extreme value, so we're gonna take the extreme value into consideration because we're gonna use that number minus x bar, and also x bar, y bar. They're sensitive to the outliers as well as the standard deviation. So that means R is also R, like the correlation coefficient, is also sensitive to outliers. Those are the important properties for correlation coefficient. And one more thing here. So the larger the absolute value of the R is, that means a stronger linear relationship and linear association. And when R equals 0, that means almost no linear association. Let's look at one example here for the calculation. So example for the house price data. So we have the formula, how to calculate the correlation coefficient. So x and y, list all those information here, and then we can calculate x minus x bar over sx and y minus y bar over xy, and then the product. So we need to take the sum of all those and divide it by n minus 1. So the sum of this column give us 6.3041, which is here, right? And divided by 1, 2, 3, 4, 5, 6, 7. So we have 8 pairs, n equals 8. So 8 minus 1, that's 7. And then R is 0.9006, 0.9006. So which is all very close to 1, right? So positive 1. That means x and y, they have a strong linear association, linear relationship. So if we want to use the calculator, so now here let's introduce this R calculator. So in our calculator, we need to type in the data. So x equals C open parentheses, and then put all the data in with comma to separate all the data and close the parentheses. That's how we type it in. So x, same thing for y, right? Y equals C open parentheses, and then type all the data in, starting from 400, 426, until the last one, 455, close parentheses. And then when we calculate correlation coefficient, so COR represent the correlation coefficient. So COR XY, open parentheses, close parentheses, and then use comma to separate x and y. So that's how we tell this calculator to calculate the correlation coefficient. So that is 0.9006. Okay, let's look at one more practice problem for calculating the correlation coefficient. So let's say we only have 3 pairs of data and x and y. So x take value 2, 4, 6, and y take value 4, 8, 12. So we first need to know what is x bar. So that's 4, and what is y bar? What is sx? Which is 2. So y bar is 8, I believe, right? Here's the tap rule. Y bar is 8 because sum of y equals 4 plus 8 plus 12, which is 24. And then y bar equals 24 over 3, so that's 8. So that's how we get y bar equals 8. And then sy is 4. And then how to apply this formula to calculate correlation coefficient. So 1 over n minus 1. So n equals 3 because we have 3 pairs of data, right? So that's 1 over 3 minus 1, n minus 1. And then we're going to expand this, right? 3 pairs. So we're going to plug in x1. So that's x1, x2, x3, y1, y2, y3, right? That's x1, and 4 is x bar and over sx. And that's y1, and then minus y bar, that's 8 over sy. And then x2, that's x bar over as x, and that is as y. That's y2, 8, right? And then minus 8, that's y bar. And then 6 is x3, x bar is 2, x is 2, and then y3, which is 12, minus 8, which is y bar, and 4 is as y. So then we have what? So 2 minus 4, and that's negative 2 divided by 2, negative 1, right? So that's negative 1 times 4 minus 8, negative 4, so negative 1, right? Negative 1 times negative 1 plus 1 times 0 plus 6 minus 2, that's 4. 4 divided by 2, that's 2, times 4 divided by 4, 1. And don't forget 1 over 2, right? 3 minus 1 in front. And then we have, that's 1 plus 0 plus, so negative 1 times negative 1, that's 1, plus 0 plus 2, right? So that's 3 over 2. So 1.5. If that's what we got for the R, then we know the calculation is wrong, because R can only be numbers between -1 to 1. Then we're gonna go back to the calculation process to look at what is wrong there. So let's get the calculator involved, and then first let's double check whether we got the mean and standard deviation calculated correctly. So x equals 2, 4, 6. The average is 4. So x bar is 4. Standard deviation is 2, no problem. And then let's type in y equals 4, 8, 12. So y bar is 8. No problem. And standard deviation of y is 4. Okay, so those are no problem. And then let's look at the formula. So we have 2 so for x we have 2, 4, 6. And then x bar we have 4, right? So 4, that's a 4, and that's a 4. So here's a type row. I think that's the problem why we got the calculation wrong. And then for y, let's check it again. Just make sure. So y is 4, 8, 12, and minus y bar, so 8, 8, 8, no problem. So 2, 4, 2, 4, 2, 4. Okay, now the formula is correct. So we got -1 times -1 plus 1 plus, that's a 0 actually. So 0 times 0. And 6 minus 4, that's 2 divided by 2. So here should be 1. And times 1. Okay, so we got 1 plus 0 plus 1. So that's a 2. So altogether, that's 2. 2 divided by 2. So that's 1. Okay. So now we got the correct calculation. R is 1. So we got a perfect positive linear relationship when R equals 1. And then if we draw a scatter plot, we can see that actually. Because it's a perfect straight line here. So X and Y, 2, 4, 6, and then 4, 8, 12. So the pairs is 2, 4, and 4, 8, and 6, 12. And then if you connect that to a line, that's a perfect straight line. So all the points lies on the line. So that's why we say it's perfect positive linear relationship. Okay. So also note the following: the correlation coefficient is not resistant. So that means sensitive to the outlier. We kind of discussed that already. And another thing is correlation is not causation. So when two things are correlated, doesn't mean one cause the other one. There might be something in between that lead to the correlated association, but that is not causation. Okay, so that's all for section 4.1. In this video, let's stop here. And the next one, we'll talk about section 4.2. Okay, thanks for watching.